We would like to prove part D of the theorem, which says the limit of a product is the product of the limits. So if the limit of f of z is wf and the limit of g of z is wg, then the limit of f times g is wf times wg. A very natural result, and we're going to use the definition of limit to prove it. So we want to show that given an epsilon greater than 0, there exists a positive number delta such that if z minus z0 is less than delta and positive, then the difference f of z times g of z minus wf times wg is less than epsilon. So what we have to start with are two limits. The limit of f is wf and the limit of g is wg. So what we know is that given any number epsilon prime positive, there exists, I missed an I there, there exists a delta bigger than 0 such that if z minus z0 is less than delta in modulus, then f of z minus wf is less than this epsilon prime, and also g of z minus wg is less than epsilon prime. We will end up choosing epsilon prime so that when z minus z0 is less than delta, this inequality that we need here occurs. So let's see how we can relate this inequality to these two inequalities. This is the one we need to show, and these two are given. So let's take the one that we need to make a conclusion about and see how it relates to the two that we know that are given. So f of z, g of z minus wf wg, we can write this in the following way. We could add and subtract a term. So we're going to subtract f of z times wg, and then we're going to add that back on, f of z times wg, so that's just 0, and then minus wf wg. So those are equal because we've just inserted 0 here. And now at this plus sign, we will use the triangle inequality. So this modulus is less than the modulus of the first terms before the plus sign, f of z, g of z, minus f of z, wg, plus, and then the terms after the plus sign, f of z, wg, minus wf, wg. Now here we have a common factor of f of z that we can factor out, and the modulus of a product is the product of the moduli. So we can take the modulus of f of z times the modulus of g of z minus wg. And here we have a common factor of wg that we can take out. And we have f of z minus wf here. And this is very nice because this difference and this difference, these two differences, are exactly these differences here that are less than epsilon prime. We need to make a comment here about the modulus of f of z. Let's do that off to the side. modulus of f of z is equal to the modulus of f of z minus wf plus wf, and that's less than or equal to the modulus of f of z minus wf plus the modulus of wf by the triangle inequality. And this one can be made as small as we like. It can be made less than epsilon prime, but let's just say that we're only interested in making it less than 1. So let's put a 1 there. So the modulus of f of z, if delta is small enough, can be made less than 1 plus wf. And let's put that in here. So this is less than 1 plus the modulus of wf times this difference, which we can make less than epsilon prime. Let's put epsilon prime in there. Plus the modulus of wg times this one can also be made less than epsilon prime. And this is equal to, if we factor out the epsilon prime, it's 1 plus modulus wf plus modulus of wg times epsilon prime. So we can make the difference that we're interested in less than this quantity, which will be less than epsilon if epsilon prime, well, it'll equal epsilon. Well, we'll just say, okay, epsilon prime is less than epsilon over this quantity here, this positive quantity, 1 plus wf plus modulus wg. So there we are. So if we choose delta, such that these two conditions hold, and also we need this one to be less than 1 as well. So we can choose delta so that this difference is less than both epsilon prime and 1. Assuming epsilon prime is a tiny little number, then of course it's also less than 1 at the same time. But technically speaking, this has to be considered separately. So there exists a delta such that all three of these inequalities occur, and therefore this difference here is going to end up being less than epsilon as long as we choose this epsilon prime number, which we can choose to be whatever positive quantity we want. We can choose it to be any positive quantity less than this positive real number here. And that means that this difference is less than epsilon, and so this limit is as we claimed. And that concludes the proof.